Welcome to the deep dive. Today, we're heading to the moon. Well, not physically, but we're diving into humanity's big push for, sustained presence there.
Right. We're talking NASA's Artemis, China's ILRS project, ESA's Moon Village idea.
Exactly. All aiming for that South Pole Aitken Basin region, mostly. It's a huge undertaking.
It really is. And the core vision, this idea of living and working there long term, runs smack into one massive hurdle.
Which is?
Power. Continuous power. I mean, how do you keep everything running? Lights, life support, experiments through that brutal 2-week lunar night.
Yeah, that darkness. It's long. Solar panels are great, but not for 2 straight weeks. And batteries alone, well, they just don't have the juice for that long, not at the scale needed.
Precisely. It's been a real showstopper for sustained missions.
But there's this solution emerging, one that feels a bit sci-fi, but is actually pretty elegant.
You're talking about the nuclear reactor and Stirling engine combo.
That's the one. Space Nuclear Reactor Power Systems, SNRPS. High-efficiency Stirling engines hooked up to compact nuclear reactors.
It's a really smart pairing. Stirling engines themselves are amazing, incredibly efficient. They basically use a heat source, almost any heat source, to move a gas back and forth in a sealed system, generating power.
Okay, known for efficiency. But what was the holdup for using them reliably in space?
Well, the theory is great, the ideal thermodynamic cycles. But predicting how they'd actually perform in the real world, especially in space, that's been tough.
Why is that? What makes space so different?
It's all the messy real-world stuff. Subtle heat leaking out where it shouldn't, the working gas not flowing perfectly smoothly, tiny mechanical issues. These things that idealized models often ignore or simplify.
So the gap between the textbook diagram and the actual engine humming away in lunar dust.
Exactly. You need precise predictions for space missions. You can't just overbuild everything massively.
Yeah.
Weight and reliability are paramount.
Right. So this brings us to the core of today's deep dive. The work by Professor Shandong Yang and his team. They're based at Chengdu University of Technology and the Nuclear Power Institute of China. What did they figure out?
They tackle that prediction problem head on. Engineers knew about these energy loss factors, these inefficiencies. But Yang's team developed a way to model their combined effects much, much more accurately.
Okay, an optimized model. What kind of real-world complexities did they manage to bake into it?
They integrated several key things. First, shuttle heat loss. That's heat sort of sneaking between the hot and cold parts of the engine because the displacer piston moves.
Okay, unwanted heat transfer. Makes sense.
Then there's seal leakage. Even tiny amounts of the working gas escaping past the seals over time can degrade performance.
Right, you need it perfectly sealed, ideally.
Ideally, yes. And flow resistance, basically. Friction as the gas moves through the regenerator and heat exchangers. It's never perfectly smooth.
Okay.
And a really crucial one, finite piston speed. The pistons don't move instantly, like in the ideal models. There's inertia, slight delays.
So accounting for the fact that things take time to move, even pistons.
Exactly. And all these subtle effects add up, especially when you need high precision and long-term reliability. Yang's team built a unified analytical model that accounts for all of these interacting factors.
So it's like moving from a blurry sketch to a high-resolution photo of how the engine will actually behave.
That's a great way to put it. It lets engineers see much more clearly how changing a design choice, like, say, the material in the regenerator or the type of gas used, will impact the actual power output and efficiency.
And they didn't just build the model, they tested it.
Yes, and this is key. They validated it against actual experimental data from NASA, specifically from the GPU-3 and RE-1000's Stirling engine prototypes.
Now, why those specific engines? What's their story?
Well, the GPU-3 and RE-1000 weren't just paper designs. NASA actually built and tested them decades ago, specifically exploring Stirling engines for space power, including potential lunar missions.
So real hardware, real test data.
Precisely. So when Yang's model could accurately predict how those engines performed in reality, it showed the model wasn't just theoretical math. It was a tool grounded in actual engineering results. It gives it real credibility.
Okay, that validation seems critical. It moves it from interesting research to a practical tool engineers can actually use to design better systems.
Exactly. It bridges that gap we talked about between the ideal concept and the practical nuts and bolts reality of building something that has to work flawlessly for years, 500,000 kilometers away.
So what does this breakthrough mean, practically speaking, for getting humans back to the moon to stay? For Artemis, ILRS, the Moon Village?
It means much higher confidence in the power systems. Engineers can design reactors and engines that are more optimized, likely lighter, more compact, potentially more efficient because they don't need quite as massive safety margins built in to account for performance uncertainty.
Less uncertainty means more refined designs.
Right. And knowing you'll actually get the power predicted is crucial for mission planning, for safety, for ensuring astronauts can survive that long lunar night and operate complex equipment.
Yeah.
It makes these ambitious long-term bases much more feasible.
So just to recap this core idea for you listening, Professor Yang's team has developed a significantly improved way to predict how these vital Stirling engines will perform. It's not just theory. It accounts for real-world energy losses.
Things like shuttle heat loss, seal leakage, flow resistance, the finite piston speed.
Right, all those crucial factors. And critically, it's been checked against real data from NASA's past work. It makes designing reliable power for the moon much less of a guessing game.
Absolutely. It's a fantastic example of applying fundamental physics and clever modeling to solve a really difficult practical engineering problem.
And you mentioned earlier that space tech often finds its way back to Earth. Does that apply here? Could these advanced Stirling engines have uses down here?
Oh, definitely. The potential is significant. Think about it. Highly efficient, potentially very reliable engines that can run off various heat sources, coupled with compact heat sources, not necessarily nuclear for all Earth apps, they could be ideal for remote power.
Like off-grid locations, research stations.
Exactly. Or disaster relief zones, where you need reliable power fast when the grid is down, maybe even powering isolated communities or critical backup systems. The drive for robustness and efficiency in space often leads to tech that's incredibly useful in demanding situations on Earth.
It's a classic spin-off effect.
Right.
So what's next for this research? They've nailed the steady-state performance prediction, but engines don't just run constantly at one level, do they?
Good point. The next big step is modeling the transient operations,
Meaning,
meaning startup, shutdown, how the engine responds when the power demand suddenly changes load fluctuations. Understanding how the whole system, the reactor and the engine, behaves during these changes is vital.
especially managing heat, I imagine. You don't want things overheating or cooling too rapidly.
Precisely. Maintaining thermal balance during those dynamic phases is critical for integrated systems, particularly in space where you can't just open a window if things get too hot. Reliability across all operating modes is key.
It really makes you think about the level of engineering required. These things need to work autonomously, perfectly, for years on end in an incredibly harsh environment.
That's true. The demands are extraordinary.
Which brings us to a final thought for you to ponder. Given this incredible precision and ruggedness needed for power systems on the moon, or maybe Mars, what could we learn from that? Could we apply some of those design principles, that need for resilience and independence, to make our own energy grids here on Earth, maybe even in cities, much more robust and less reliant on single points of failure?